Hello. So let's continue with our lecture on rigid body motions. So in the last lecture we studied the definition of rigid body motions, which is that if I have points A and B, then the length before the transformation is the same as the length after the transformation. That's the definition. And then we did an example, and the example was translation, and translation is defined as a point A gets mapped to the point A plus T, and you can think of T as the shift. Okay, in today's lecture we'll focus on rotations. And what I'm going to do is to try to formally define rotations and just give you the mathematical underpinnings of working comfortably with rotations. So rotations have two main properties. First, they are linear transformations. What do I mean by linear transformations? So a linear transformation, if I have points, suppose A gets mapped to psi of A and B gets mapped to psi of B, then if I have the point alpha A plus beta B, that should be mapped to alpha psi of A plus beta times psi of B. This is the definition of a linear transformation. Okay, that's one way to think about it abstractly in a mathematical sense, but there is a more practical way to think about it, which is that suppose A is a vector another way is that psi of A is given by a matrix times a vector A. So here let's get our notation right. This is a matrix and this is a vector. Okay, let's take up another, let's state this more clearly. So suppose we have points in R2. Then A is a vector, e.g. A1, A2. And any linear transformation corresponds to a matrix multiplication. So let me indicate this by psi of A is going to be some matrix. Let's use B11, B12, B21, B22, multiplying this vector A. So in other words, the vector A, if we multiply by some matrix B times this vector A, we get the result of this linear transformation. And what we can show is that any linear transformation can be expressed by such a matrix multiplication. So we can think equivalently with in this matrix notation. So I like to have my points are going to be column vectors. And so if we have transformations, linear transformations from two-dimensional space to two-dimensional space are represented by 2 by 2 matrices, as here. And if we are in three-dimensional space, then a point is of type B1, B2, B3. So it's a column vector. And any linear transformation from R3 to R3 corresponds to multiplication by a 3 by 3 matrix. So we might have a matrix A11, A12, A21, A21, A22, A23, A31, A32, A33, and then we have B1, B2, B3, and this gives me some new column vector. Let's use the notation C for this, C1, C2, C3. So this corresponds to C is the product of matrix multiplication in this way, and is the matrix, A here is the matrix corresponding to the linear transformation. Okay, so this is just standard linear algebra. Any linear transformation can be expressed by a matrix, and matrix is obviously a linear transformation. So let's go back to rigid body motions. So we want to understand rigid body motions that are also linear transformations. Okay, how do we do that? So, I mean, so we need to somehow study the condition of rigid body motion and add that condition to that of being a linear transformation. So we're going to add a little definition here. An orthogonal transformation is a linear transformation that preserves inner products. So that's the definition of orthogonal transformation. So suppose we had A and we had B, and A gets mapped to psi of A and B gets mapped to psi of B. What do I mean by inner product? So the inner product before the transformation is given by A dot product with B, and the inner product after the transformation is given by psi of A dot product with psi of B, and these two are equal. And for those of you who've forgotten what I mean by inner product, A dot B is also called scalar product. So if A is A1, A2 and B is B1, B2, and I've expressed them as column vectors, then A dot B equals A1, B1 plus A2, B2. Okay. So this is the definition. So essentially what I'm saying is inner products are preserved. Any transformation which has this property, any linear transformation which has this property is called an orthogonal transformation. So let's try to understand this, some properties of orthogonal transformations. One property is that orthogonal transformations preserve norms. So if I had point A, okay, so what do I know? If I have A, that gets transformed to psi of A. And let's consider now again the point A, and that gets transformed to psi of A. Now consider the dot product before the transformation. That is going to be A dot A. So this is before. And now let's consider the dot product after the transformation. Psi of A dot psi of A. And this is the dot product after the transformation. Okay, and by the property that this orthogonal transformation preserves norms, what do we know? These two must be equal. Okay, then let's write this out. This means that norm of A squared equals the norm of psi of A squared. So clearly the norm is being preserved. In other words, length is being preserved. So this might lead you to think that orthogonal transformations are consistent with the concept of rigid body transformations. But let's prove this more generally. So what we have to do now is to show this. So more generally, we're going to have some point A, and this point is going to get transformed to psi of A. We're going to have a point B, and that's going to get transformed to psi of B. And what do we need to show? We need to show that is equal to if psi is an orthogonal transformation. So that's something to be proved. So how do we prove this? So let's do the following. Let's consider the length of psi A minus psi B. And what is that going to be? So this is going to be so that's the length of psi A minus psi B, and the question is this equal to the length of so we don't know whether this is true, but that's what we'll try to prove. If we can manage to show that the two of these are equal, we are in business. So we can expand this out. So I'm putting a question mark here to imply that we don't know whether this is true or not. So what do we get? If we expand this out, we are going to get so that's what we get on the left hand side, and the question is this equal to what we get on the right hand side? Okay, now let's make some observations which we'll do on the side. So we had earlier showed that and we had showed that okay, we showed this on the previous page. So that's good. So and what else do we know? We know that psi of A dot psi of B is equal to A dot B. So these are all true, and one of these is true by definition, and these were proved, and these two were proved previously. Okay, so now we are in business. We are trying to ask the question, is this expression equal to this expression? Okay, but we have, and we can use some properties here. So we just showed that psi of A squared is equal to A squared. So the length of psi of A is the same as the length of A. So this enables us to cancel this guy. These two guys are the same. The length of B after the transformation is the same as the length of B before the transformation. So therefore this and this are the same. And we also showed that psi A dot product with psi B is the same as A dot product with B. And therefore this term and this term are the same. And this is great, excellent. So we are very happy because we have just shown that these two are equal. So in other words, we have proven this result. Okay, but what does this mean? What this means is that therefore psi is a rigid body motion. So let me summarize the result. So the result is that an orthogonal transformation is a rigid body transformation. So just to remind you, we started with the definition of orthogonal was that it is linear and it preserves inner products. Okay, so in other words, A dot B equals psi of A dot psi of B. And the definition of rigid body transformation was that the length of A minus B is the same as the length of psi A minus psi of B. And what did we prove? We proved that orthogonal transformations are rigid. Are rigid body transformations. Okay, and recall that earlier we proved that translations are rigid body transformations. So thus we have two examples of these.